Next, let's consider the measures of variation. Measures of variation, if you recall, are used in order to measure the amount of variation in the observations that we have collected on a variable. And these measures are range, interquartile range, mean absolute deviation, variance, standard deviation, and coefficient of variation. But before checking the calculation of these measures in R, let's see how can we compare and see which variable actually having more variation graphically. For that, I first generate two variables which are identical in every aspect apart from the amount of variation that they have. And for that, I set a seed. Guys, don't be confused with this. Since I'm generating random numbers, set a seed fixes those random numbers. The first variable, I call it x1, is R norm. I use 1000 observations with the mean 0 and standard deviation over 3. And the second one, I call the x2, R norm. Again, 1000 observation, mean 0, standard deviation is equal to 5. Now, these two variables are identical in all aspects apart from the standard deviation, that x2 is having higher standard deviation. And from the lectures, we know that a higher standard deviation is an indication that the second variable is having more variation. Okay, let's run all of them together. Okay, now in order to visualize the amount of variation and to compare the amount of variation between these two variables, by plot density of x1, and let me use a color for it so that we can easily identify this is red, and let me add the density plot of the second variable x2, and let me color it by blue. Okay, let's plot the two. Now you can see the red one, the red graph is x1, whose standard deviation is 3, and the blue one is x2, whose standard deviation is 5. The mean of both variables it's 0, which is located in the center here. Now, if you compare the two graphs, the red one and the blue one, you see that we have more variation in the blue one. And if you check the red one, the density is more compact around the center, but the blue one, the density is more spread around. Graphically, we can see that x1 has less variation than x2. Now let's see how we calculate different measures of variation in R. Let's start with range. First one, range. The range of x1, for example. The range of x1 starts from -9 and ends at 10. And the range of x2 starts from -16 and goes up to 19. Now, if you compare the range as well, you see the range of x1 is a shorter interval compared to the range of x2. Quantile range. The interquartile range is an interval which starts from the first quantile and ends at third quantile. So in order to construct the interquartile range, I call it IRQ for x1 for 1 is C of first quantile is nothing but quantile x1 0.25, the first quantile, and ends at quantile x1 0.75. So this is interquartile range. If you want to see Q1, let's run this and see what is this. You see, the interquartile range for the variable x1 starts from -2 and ends at 2.1. So the same thing we can calculate for x2. I just copy everything together and paste it here and change x1, this one to 2, this one to 2, and this variable x1 to x2, and this one also x1 to x2. Now, if you run these two values together, now you see the interquartile range for x2 starts from -3 and ends at 3. Again, the interquartile range of the second variable is lengthier than the first variable, indicating that we have more variation in the variable x2. An important application is application of interquartile range is to construct an interval around it that does not contain outliers or extreme values. Consider the variable h. If you plot the density of this variable, now you see that on the graph we have outlying values, and if you recall, we had problem and specifying the center for this variable because of this extreme or outlying values. Now, with the help of interquartile range, we can construct another interval around interquartile range that does not contain outlying or extreme values. And for that, I need, in order to construct the interval around the interquartile range of the variable h that does not contain the outlying values, first let's find the length of the interquartile range. And that is nothing but quantile xh 0.75 minus quantile xh 0.25. This is the length of the interval, the interquartile. Now, for constructing that interval around interquartile range, we need a lower bound, which is Q1, which is quantile xh 0.25 minus 1.5 times length of interquartile range. And the upper bound is quantile x 8.75 plus 1.5 times this range times this LIQR. Okay, these are the lower bound and upper bounds of the interval which does not contain outlying values. Okay, now we need to define the new variable yh. I call it yh is xh such that xh is bigger than the lower bound, bigger than or equal to the LB, and xh lower than or equal to this value, less than or equal to upper bound. Now plot the density of the new variable yh. You see that there is no outlying values. That means the yh, which is this variable, containing all those observations in xh such that those observations are bigger or equal to the lower bound and less than or equal to the upper bound. By taking all those values in this interval, we practically remove all extreme or outlying values. Now, if you check here the graph of this new variable yh, we see that there is no outlying value, and the center of this should be somewhere around 24. You can check that by calculating the mean of yh, which is 24.6, and if you calculate the median yh, which is also 24. Now you see the value of the mean and the median are very close now. And that means the true center of the variable h with the outlying values being removed is around 24. Next, let's consider the mean absolute deviation. The mean absolute deviation math is of x1. Let me go back to the variable which I have defined myself, with center being the median of x1, which is 3.09, and the MAD of, let's see what is the MAD of x2, center is equal to the median of x2, sorry, which is 5. The variable x2 is having a higher variation. The next measure was variance, and if you remember, I told you that in the class that the variance is having a interpretation problem. Nevertheless, let's see how we calculate the variance of x1, which is 8 point something, and the variance of x2, which should be a higher number. Now you see the variance of x2 is 27, the variance of x1 is 8, but we cannot interpret these two numbers. Nevertheless, it shows that x2 is having a higher variation. Next, standard deviation. We have used the standard deviation in order to remedy the problem which variance has. The formula in R is SD of x1, which is 2.9, and SD of x2, which is 5.2. Normally, the interpretation of standard deviation and mean absolute deviation, it's very close to one another. Computationally, they are having differences because one is using the absolute value, mean absolute deviation is using an absolute value in order to find the distance of each observation from the center. And standard deviation is finding the square of the distance of each observation from the center. Therefore, their values are not identical. The last measure that we have studied was the coefficient of variation, and I told you that coefficient of variations is particularly useful when we want to compare the variation of two variables having different units. Compare the amount of variation in the salary and against the working hours. Let's go for the salary first. CV of salary is nothing but the standard deviation of salary, x salary, divided by the mean of salary, mean x salary, and CV of working hours. That is nothing but the SD of x working hours divided by the mean of x working hour. Run this CV salary. Let's see how much is this, 0.28, and CV of working hours, that is 0.11, meaning that the amount of variation in the variable salary, it's higher compared to working hours. Differences in the salary is much higher than the differences of the working hours.